Okay, so let's go on our class on multiple integrals, and our next topic is going to be about substitution, and I believe you already know quite some things about this. Okay, so let's see. We can begin with a function from R2 to R, and so we are integrating on some domain U of R2, and we have some function of two variables with real values, and we want to calculate the integral, the double integral of f on this area, on this domain. Okay, so let's see a bit more precisely. So you already know that if we want to perform a substitution, we are going to need a well-defined substitution. So let's write it this way. You have the variables x, y, and you have new variables uv, and they are related by this relation. Phi of uv is xy. So basically x is can be defined as x of uv, and y is defined as y of uv, and that's what gives you the function. You can see it in that direction, or if you know that it's going to be a valid substitution, if the process is reversible, so you can find a phi minus 1 such that from x and y you get the uv variables. Okay, so first remember that your substitution is going to be valid if it is defined by a reversible function, so an invertible function. And now we know how to maybe qualify invertible functions because we have this local and then global inverse theorem. So that's one thing. So what do we have? You have your function f defined with xy variables, and you want to integrate on um, domain U. Thing is that you realize that if you substitute the xy variables into new variables uv, it's going to make it much simpler. So what should we do? First, you have to remember that substitution in integration has 3 steps. Whether you have substitution, whether you're in one variable or several variables function, it's always have 3 steps. First, well, in any order you like, as long as you perform them all, you change the domain of integration. Okay, the domain of integration has to be expressed with respect to the new variables. Okay, so you have, if that means that x, y belong to domain U, they are going to belong to some other description of the domain in terms of UV. Okay, so for instance, if I tell you that I want to work on a half circle, half disk in the plane, right? If I tell you that I want to work on this area of my plane, I can describe that in Cartesian coordinates by saying that x is between -1 and 1, and y is smaller, well, y should be bigger than 0 but smaller than well, you know, this thing here can be described as square root of 1 minus x2. Okay, and that's describing you that half disk. But if you want to talk about polar coordinates, you know that this is going to be very easily described in polar coordinates. It still represents the same geometrical locations, but in terms of polar coordinates, it would be written as rho is smaller or equal to 1 and greater or equal to 0, but that's goes as that's natural because rho is always positive. And we should have theta that belongs to 0 pi. Okay, so you see it's the same geometrical location, but it has to be expressed in with different bounds, right? So that's why the first thing that you have to consider when doing a substitution is to see what's happening for the bounds. How do they change? How does my description fit with my new coordinates. So that's one thing. Second thing you have to do when you're performing a substitution is change the function. Okay, your function was expressed as f of xy, and now it's going to be expressed in terms of new coordinates uv. Okay, so if I want to write it, it's usual to write a new function, but the idea is that you've got this correspondence that f of x, if x depends on uv, y depends on uv, that's going to be giving you a new function that we call f tilde, which is a function of two variables of uv. Okay, or if you express u and v as sorry, functions of x and y, you have the same relation. Okay, so second, change the function. And finally, last step, don't forget to change the infinitesimal term. Infinitesimal term, and more on that name later. What do I mean by this? Here it's going to be the dx dy. That has to become some du dv, but you already know that that's going to come with something in front of it, which happens to be the determinant, value of the determinant of the Jacobian matrix of the transformation. Okay, so let's dig a bit more into where this formula comes from. Okay, but really don't forget the 3 steps for a substitution in any order you want, but you have to perform them 3: change the domain, change the function, change the infinitesimal term. Okay, so let's understand where this formula comes from. First, let's go back to integration in one variable. So what's the notation you want, you are used to? So let's say you have some function f of x and you integrate with respect to x, and that's between some values a, b. Okay, and let's make f a positive function. That's going to be the beginning of it. All right, so that's what is called the integration you are used to perform, to use, is called the Riemann integral. It was theorized by Bernhard Riemann. It was big. It was the middle of the 19th century. I think something like 1854. And what does it say? All right. So the idea is that if you've got interval AB, and we said that we want f to be a positive function, whatever it is, so that would be y is equal to f of x. What is the integration for? It's going to be to calculate the area below my function f. Okay, so that area here. All right. The thing is, how do we proceed? You proceed exactly how you would do if you wanted to approximate this area with maybe a computer or by drawing. What would you do? You would take some small intervals, okay, and make some rectangles out of with using the values of the function, so something like this. All right, so you've got some small rectangles, and maybe you remember that, maybe you've seen that in year 1. We are approximating our function, which is what is called a step function, by a step function. Okay, why? Because it looks like some steps. All right. What is good with this approximation with a step function? It's that now if I want to compute the area below my step function that approximates my function, it's going to be very simple. Why? Because these are just areas of rectangles. Okay, so that area is very simple to compute. Let's say that all my intervals have a small delta x. So that's a delta, that's not a rounded, that's a delta. Delta x size, so size of the interval. And let's say that to make my, to create my, let me get back there. To create my step function, I'm choosing one particular value. I'm taking the function f of a plus k times delta x. What do I mean by this? F of a plus k times delta x. If this is the first approximation, I'm going to take k is equal to 0 and I take the value of my function at that point. If I'm looking at my second rectangle, the one here, okay, the second rectangle, the one here, I'm going to take the value of f at a plus delta x. If I'm looking at the kth, if that is the k times delta x, a plus k times delta x point, I'm just getting the value of a at a plus k times delta x. Okay, so now it's going to be very simple to add areas of rectangles. We are adding areas of small rectangles. Okay, and all my areas are going to have the size, the width of the bottom part of my rectangle is going to be delta x times the value of my function. So one small rectangle is going to have this this value. Okay, so now if I want to approximate my area between a and b of my function f, that's going to be, I'm going to sum all my small rectangles. So that's going to be the sum for k is equal to 0 for f of a up to, well, I don't know, let's say I've got n rectangles. So my last rectangle is going to be n minus 1. So so up to n minus 1, f of a plus k delta x times delta x, right? So that's going to be an approximation by summing those areas of small rectangles. Now, the approximation is going to get better and better as delta x tends to 0. I have smaller and smaller widths, and I've got a better and better approximation. Okay, so locally you can view that. If your function is looking like this, maybe with some big delta x, you're going to get this approximation, right? And with a finer one, so you can choose the first value, you can choose the last value. Well, these are all different kinds of approximating this area, and in the end they will all converge to the same value, which is, if you refine, let's say you take half of this size, you're going to get a better and better, maybe I should take a more contrasting color. So that's going to be my first one. I'm just taking intervals of size 1/2 my previous size. Okay, so that width is going to be half of the first width, and you see it's going to give you a better approximation than the first one. So the idea is that as delta x tends to 0, that value here is really going to converge to the real area below the curve, and that's what is expressed by the notation that that this area is given by, that's like a continuous sum, because we have taken our delta x to be so small that it really gets to the limit value is going to be continuous. The delta x, well, now we're going to use that notation dx and the value of your function f of x between a and b. Okay, so that was just a notation to begin with, this integral notation, and that dx stands for infinitesimal size. Okay, So that's where it's coming from. It's really to tell you how it's going to make the size of the rectangle you are using.